It's like, oh, we're out of time. I have to cover 3 topics and I only have 1 week left. All right, well, there goes partial fractions. Yeah, they're going to forget it before Calc 2 anyway. You know, so I just kind of have to operate under that assumption. Actually, both ways, because you either didn't learn it or you learned it and you forgot it anyway. So, partial fraction decomposition is one of those unfortunate topics that it takes a beating in terms of reputation, because people hate it for some reason. But I think they only hate it because of the algebra involved. Right? It's pretty straightforward. It's very procedural. One of the byproducts of this concept is that it kind of looks like U substitution involving natural art. It kind of looks like a trig substitution. It kind of looks like a lot of things. And so where partial fractions gets its bad reputation is when you get your test back and you lost a bunch of credit on the question because you thought it was something else. You didn't even attempt to solve using partial fractions because you didn't even know that that's what the problem was related to. All right, that's where people get pissed off. Yes, but sometimes you take an approach, let's say we did a trig substitution, you go through that whole approach, convert it over into trig form, and you get, let's say, I want to make sure I come up with 1 over secant cubed sine to the 4th. And you're like, okay, I can get an answer. I gotta do like 13 different trigonometric identity substitutions, but I can get there. Is this the best way to go about it? You know? Turns out that oftentimes the best way to go about it is partial fraction decomposition. What partial fraction decomposition is ungetting a common denominator. Right? So what that means is that there were 2 fractions that were separate before. Somebody in an algebra class multiply top and bottom of the 2 fractions by something to get a common denominator, and then put it together and simplify the tops, and came up with this. Sometimes you can pull 2 fractions apart just by looking at it. Sometimes you can't. Right? But it is all going to start with the factors related to the denominator. Right? Because if you're getting a common denominator, it's coming from those common factors. So we start off, and we're going to pretend this integral symbol isn't even there for now, because it's not even going to be relevant until the very last step. So I'm going to factor the bottom. What, plus 5 minus 2? And, you know, like while I'm at it, I'm going to take a look and see if there's a common factor top to bottom, because sometimes it isn't even partial fractions. Sometimes it's just a matter of factoring and canceling in common factors and just using some other simpler technique. Right? Not the case here. We have 2 distinct linear factors. All right, so what we're going to have here, and you can look at the table above, but we're going to have, I'm going to just take this and write it with a little arrow here, 4x plus 41 over x plus 5, x minus 2. If we're going to unget a common denominator, then what we're looking at are 2 fractions, each of which having one of the factors as its denominator. I just have to figure out what the numerators are so that when I get a common denominator and put it all together, I would come up with 4x plus 41. All right? So how do we determine that? Numerator divided by the other factor. You could, and that's actually the basis of one of the ways of decomposing partial fractions. But So let's actually think of it this way. If I were taking these two fractions and putting them together, I would multiply top and bottom of this fraction by x minus 2, right? I'd multiply top and bottom of this one by x plus 5, right? So I would have an x in each part, an x to the first power. I have an x to the first power in my final answer. So I could only really be differing from what I have here by some sort of constant on the top of each fraction. All right, so it really is, I mean, I'm already going to have the x's where I want them to be. It's just the numbers that make the 4 and the 41, that's what I really need to work with. All right, so what that's telling me is that I need a constant that I'll call a for this fraction, and a constant that I'll call b for that fraction. All right, a little nifty trick. Always drink water. The degree of your numerator should always be 1 less than the degree of your denominator. Basically, if you were to take the derivative of your denominator, what type of function would you get? That's the model that you should be following to give you your numerator. So if I took the derivative of x plus 5, I would get a constant. So put in a constant. If I took the derivative of x minus 2, I'd get a constant. So put in a different constant, use different letters, however you want to do it. A sub 1, A sub 2, if you want to go subscripts. But that's the gist of it. All right. So then what I'm going to do is solve these for a and b. And I'm going to do that by clearing out all the denominators. So I'm going to multiply everything by x plus 5, x minus 2. So I'm looking at 4x plus 41 is equal to a times x minus 2 plus b times x minus 2. Some people like to do like numerical substitutions at this point. I don't like doing it that way. I like to do it strictly algebraically. So this is my technique. Distribute. Crikey. It's like a Friday afternoon mistake on a Monday. All right. So then this is how we're going to figure out our A's and B's. Not by erasing stuff, but by highlighting stuff. So anything that has an X attached to it should combine to give you the 4X. So I'll get a relationship here that 4X is equal to AX plus BX. But really that's the same, because the X would be irrelevant. That's the same as saying 4 equals A plus B. Anything that does not have an X attached to it should add to 41. So, what do I do now? Well, it is a system of equations, so we could use system techniques. I want to actually take this opportunity to show you a little calculator shortcut. It's a little linear algebra precursor, but it's nice and it'll save you from having to do any of this stuff by hand. Well, from here on out, in order to get the A and B values. So let me just rewrite this in both of them in standard form. It's really the same as saying A plus B equals 4. It's easy enough to do by hand in this case, But if you have more than just the two variables, some of these partial fraction questions can have like 5 or 6 variables, A, B, C, D, and so on. It can be pretty messy. So an alternative approach would be pretty useful. Without getting into the nuts and bolts of why this works, because that's like a week in linear algebra. We're just going to take the coefficients and make a matrix out of that. And we're going to use row reduction techniques to get it into reduced form. Okay, and what that means is that we're going to use our calculator to do those row reduction techniques. Basically, you know, if we were going to use like a multi-step process just from a different course, how is that saving us time and energy in this course? It's not. So we need the shortcut. The shortcut is to use our calculator at this point. One of those things. No, it's a fun course. I like it. Just not everybody else does. All right, so we need to get our matrix in. So this is a 2x3 matrix. In your calculator, you have a matrix enter. No matter what version you have, it's in the same place. So second inverse, and it'll bring you into the matrix. You have options for names, math, and edit. We want to go to edit. We want to tell the calculator what the matrix is. All right. When it asks you for the dimensions of the matrix, we tell it the number of rows first, followed by the number of columns. So 2, enter, then 3, enter. And then we just type in our information. When you type it in, you know, each entry, hit enter, it moves you left to right, top to bottom. So 1, enter, 1, enter, 4, -2, 5, and 41. And again, folks, this system of equations, very easy to do by hand if you needed to. I just double the first one, add it together, simplify, solve, and be done with it in like 30 seconds. But they're not all going to be this easy. Okay, very important. So, I want to actually do something with this. We're going to put it into what's called reduced row echelon form. It's the rref command. All right, so that's in the matrix under math. So I'll just quit out of here so I can work on a fresh screen. Second inverse to get back into the matrix. Then you go to math, so the right arrow to the math column. Scroll down till you find the one that says rref. Just be careful, there's one that says ref, which is row echelon form, but not reduced. Still useful, but not as useful. So this is option B. I don't know if that's the same in all calculators. So this command comes up on your screen. You need to tell the calculator what the matrix is. So we want rref of matrix A. All right, so that would be, again, second inverse, so into the matrix editor. Under names, we select matrix A. Close the parentheses or not, it doesn't make a difference. And so we get this display. And I'll run through it again with another example in a minute. But this is what your outcome should be. And it pretty much flat out tells you what the answer is. or at least what the values of A and B are. We still haven't integrated yet, but we'll get to that in a minute. Because if you think about where the entries were in the matrix that we got initially, where they came from, they were coefficient of A in the first column, coefficient of B in the second column, and then loose constants at the end. So if you want, you put it right back in that form. This is A. Well, I wouldn't want to put it there. A, B, add them together and throw in an equal sign. So it's kind of in disguise. It's saying 1A plus 0B equals -3. That's the same as saying A equals -3. 0A plus 1B equals 7. That's the same as saying B equals 7. All right. If I had 7 equations with 7 variables, it will be no more difficult for the calculator to do that than it was for it to do this. All right, so that's the hook. That's the reason why you learn to do it this way. Not to do a simple one like this. You know, you can do this algebraically. You learn it on this problem so that you can handle much more complicated cases down the line. All right, and the next one has a little bit more teeth to it, so you can kind of get a little bit of a sense. But now that we have A and B, I know what the 4x plus 41 over all that stuff is equivalent to. It's equivalent to -3 over x plus 5 plus 7 over x minus 2 dx. And those are pretty straightforward because they're each natural logs. So -3 ln x plus 5 plus 7 ln x minus 2 plus c. So almost like the trig substitution problems, we did all of that background work so that we could get something that's much simpler to integrate. But then once we got to this point, it's just natural log. Because again, if the numerator is the derivative of the denominator, then it's a natural log situation. The antiderivative would be ln of whatever the denominator is. So looking at just, for example, the x minus 2, you'd say, okay, well, the derivative of x minus 2 is not 7. It's equal to 1. Right? So if I were to say ln of x minus 2 would be 1 over x minus 2. So I correct for that by multiplying by 7. All right? But if you know, you need to, you don't have really a choice, you need to know your log rules. So a rule that comes into play here would be the antiderivative of u prime over u du would be equal to ln of u plus c.
Do it by bringing x minus 2 to the top, to the negative first time.
Yeah, but then you get that contradiction. You get something divided by 0 and it all falls apart. Just do me a favor for a question like this or trig substitution on a test. It gets really messy. Just do something like that. It'll like clearly indicate where your final answer is, because it could be anywhere. And more often than not, when I do a point deduction, it's because your answer was staring me right in the face. I just didn't see it. Right? I was following your progression, and then you just kind of put the answer somewhere where you had room, and I just never noticed it, so I took off a point. It's a point I give back, but why deal with that grief? All right, so let's tackle, well, I don't even know. It's just the quality of this thing is bothering me. So let me just get back there. There we go. This one looks pretty crispy. So we have a quadratic on the top and a cubic on the bottom. It's in disguise because it's in factored form. But if you distributed it out, it would be cubic. So one thing you might try to do is factor in the top. to see if there's a common factor that would cancel. I'll save you the time and energy on that and tell you that even if it is factorable, it's not going to be factorable in a useful way. All right? So let's just kind of jump right to it, focus on the pre-calc part of it. So that's everything except for the integral. All right, so we have a power of 2 situation here, right? So we're actually going to have 3 fractions that make up our sum. One of which would be dealing with the linear factor. Linear factor has a constant numerator. Then you have a quadratic factor, which is a little stranger. Right, and that's where you would probably want to refer to the chart. To deal with quadratic factors, well, not even just quadratic factors, but anything in binomial form raised to a power, is we take whatever the factor is without a power, and then we keep increasing power consecutively until we get to the power we're looking for. In this case, we don't have to go too far to get there. All right, so if it were x, that factor on the bottom was x plus 1 to the 7th power, unfortunately what that would mean is I would have an x plus 1 in the 2nd, to the 3rd, 4th, 5th, 6th, and 7th. You'd have this monster of an expression. Right? But we have other techniques to handle those kinds of situations. But that's one of the strange things that kind of occur, and you sort of have to be mindful of that. Right. So, and I'll just point out where that is here. That's the ax plus b to the k power. That, unfortunately, is what all this means. All right. Somehow, all of this means what I just did here. All right. But they are at their hearts, I guess, linear factors. So each one would have a constant numerator. They would just all be different. All right, so this one's a little bit more work. We're still going to follow the same idea of multiplying by the x times x plus whatever your common denominator is. So you're going to have a times x plus 1 squared plus bx times x plus 1 plus c multiplied by x. All right, so basically the components of your common denominator not accounted for in the denominator that's already there. So I already have an x, everything else. I already have an x plus 1, everything else, and so on. All right. So then I have to distribute out, clean it up, come up with my system, and then go from there. With the idea being that what I end up with is at least doable and in theory simpler than what I started with. So x squared plus 2x plus 1 plus bx so I'm just running through with the distributive property. All right, so I FOILed out the x plus 1 squared, got x squared plus 2x plus 1. Then I ran through with an a. And then I just distributed the bx against the x and the 1. And then here I distributed the a against all this stuff. All right, the idea being, again, just like the last one, that the terms involving an x squared here should add to the term involving an x squared on the left-hand side. So a 5x squared equals ax squared plus bx squared. But again, the x squares they're irrelevant. I need to know the a's and b's that'll give me a 5. I mean, you might say, well, a is 2 and b is 3. Yeah, but I might say a is 1 and b is 4. You know, there's a lot of different possibilities. So we don't want to just guess, you know. So what I'll do is I'll say a plus b has to be equal to 5. Then the terms that involve x's, a few of those. So we're looking at 20x equals 2x a plus bx plus cx. But just kind of getting it in the right format, I'm going to write it as 2a, plus b plus c is equal to 20. Then the last one, that's actually pretty simple, because the only thing that's left over on the right-hand side is the a. And the only thing left over on the left-hand side is the 6. So a has to be equal to 6. I'll write it like this. All right. So again, something you can do algebraically by hand pretty easily. Actually, very easily in this case, because you flat out already know what the a value is. But I'm going to show you the matrix approach again. So here we have 3 equations with 3 variables. Those variables would be a, b, and c. And then you have your constant. In my first equation, I have coefficients of 1, 1. There was no c, so 0. The constant is 5. The second equation, 2, 1, 1, 20. The last one, 6, geez Louise. 1, 0, 0, because there's no b and c values, and 6. So I'll do the same thing. I'm just going to use the same approach. In fact, I'm going to use the same function. In my home screen, I'm going to use the same command. So in my matrix editor, second inverse matrix, edit. This time it's a 3x4 matrix. So 1, 1, 0, 5. 2, 1, 1, 20. That's 120 for some reason. Figure that. 120. 1, 0, 0, 6. All right. So then, again, you could just use the command in the home screen, but I'm gonna pretend that we didn't do that. I'll quit out of here. Pretend this isn't here. Hit clear. Second inverse to get into the matrix menu. Math. You want to find the one that says RF. Select matrix A. So again, you're making 3 trips into the matrix editor, or matrix menu, I mean. So second inverse matrix. Select the name matrix A. And you see it's the same calculation as before, except it's pointing now to a new matrix. In this case, matrix A, which has these characteristics. So again, this is my A constant in the first column, my B variable, sorry, and my C variable. So I now know that A has to be equal to 6, B has to be equal to -1, and C has to be equal to 9. linear functions in 3 variables, that becomes kind of like par for the course in Calc 3. And so this technique is something that we'll explore in much more detail in that course. But for now, it's just like baseline. How do I put it into the calculator? This is how I put it in the calculator. I'll give you more context then. Definitely a little bit more before this course is over, but not the same kind of detail that you would get in Calc 3 or linear algebra. So we're going back to this. I now know that the a is 6. So my new integral would be 6 over x. Then -1 over x minus 1, or sorry, x plus 1. And then plus 9 over x plus 1 as a quantity squared, dx. All right. So this one's a little trickier, obviously, as you know. But even when we get to the integral part of it, there's still a little bit more work to do. Because you might look at this as a little u substitution, although I don't think it's that complicated. The first two are natural logs. So we're looking at 6 ln x minus ln of x plus 1 plus, I'm going to write this as the antiderivative of 9x plus 1 to the -2nd dx. So sometimes a problem might look like u substitution, but you would not need to use u substitution if the inner function has a derivative equal to 1. You can just integrate around it. All right, so just basically pretend that x plus 1 is just a simple variable x, in which case you would increase the exponent by 1 and divide by the new exponent. And you could verify that just by checking. But the thing that you're on the lookout for there is that if you have an inner function, if you were to take the derivative of that, is it anything other than 1? If the answer is no, then integrate around that inner function. Check by differentiating. Apply the power rule. 9x plus 1 to the -2nd. By chain rule, derivative on the inside would just be equal to a 1, so it's not going to impact it. So regardless of the fact that there's an inner function, it doesn't complicate the situation, so it doesn't require any special attention. All right. And so this, at long last, would be our final answer. But we didn't get bogged down too much in the algebra. We still had to do some algebra, but in terms of solving the system, it's just a layer that you didn't want to have to worry about. What I'm telling you is that you don't have to worry about it. Use this technique. All right. So you want to definitely familiarize yourself with this technique, because, I mean, you could even go back to old tests and quizzes from college algebra and pre-calc and see instances where that technique would have been useful. All right. They obviously didn't show you that on those levels because it would have done the algebra for you, and they were testing you on your ability to do the algebra. / they didn't know how to do it themselves, so they wouldn't have taught it to you. So.